Well, thank you very much. So I was told my first lecture would be 50 minutes, so well, you tell me when I need to stop. I'm muddled up. So yeah, this is the first of 3 lectures that I will give on subgroup, submodule, and representation growth. And I will mainly focus on these things on, well, groups. So you can imagine there might also be representation growth things for more complicated things. But I'm a group theorist, and I will sort of try to provide some of the algebraic background and leave all the kind of difficult combinatorial things to the other speakers who will sort of probably do more fancy combinatorial things than I will ever do. So I will also take the opportunity, because I'm one of the first speakers, to talk about some old and new results. And today, probably more old than new results. So old and new, let's put that here. So I'm not going to talk about many advances that I made last week, partly because I didn't make any. Well, I made some, but you're not interested in them. So, I want to talk today, first lecture, mainly about subgroup growth. Representation growth, I will probably only touch upon tomorrow. And I want to compare it. I want to have some background. So I want to compare it a bit with some other type of growth that you you probably have heard about. So something called word growth. So word growth is kind of well-studied subject in geometric group theory. And so it has similarities, and there are some interesting differences. And so maybe by looking at some examples, I also want to look at some examples. So by looking at some examples, we can sort of discover what can inspire us if we're interested in subgroup growth and what might be different, and how these things compare. Okay, so that's what I want to do. And so let's start a bit with this word growth business, because that's sort of very easy to picture. So what you do is you take a group, and to make some combinatorics or to make some kind of asymptotic group theory, you assume it's finitely generated, and you fix the generating set. So you fix the generating set, let's say x1 up to xd. So sometimes this is called a marked group, because it is a group with a fixed generating set. And it's convenient, so that's a finitely generated group. It's convenient to symmetrize the generating set somehow to include the trivial element and also inverses for my generators. So, I mean, of course, I could have done that from the beginning, but typically when we write finitely generated group, we don't pick a symmetrized generating set. We pick a short one. And then there's a natural length function. So now you can express every element little g in the group. You can express as a word, as a product of these generators or their inverses. And so there's a natural length function. You just look at shortest representations of your element as words in these kind of generators. And so there's a combinatorial kind of length function, combinatorial length, in terms of, let me just put S words. So we're trying to optimize kind of, so by writing things as short things as we can. And then there's this kind of, and of course this depends on my choice of the generating set. And that is one of the crucial differences that I want to highlight in comparison to the subgroup growth. Yeah? So in this world of word growth, which in some sense precedes subgroup growth, everything is sort of very much tuned towards the choice of the generating set. Okay, and then we get these kind of counting functions that Christoph already mentioned. So we get something that I want to call a n dot to distinguish it from the a n that we already saw. So there's a count of the number of elements in my group that you can express by writing down words in my chosen generators, group words of length that equal to n. So these are and I will drop the s now, but everything depends on s. Okay, so I'll drop it now because you see there was an Sn, and my capital S is not very distinguishable from the little s. And so if I write the capital S and the little s's at the same time, everybody gets muddled up. So I will drop the s, but it should be there. There's a ghost here that should kind of go through all the time. So equals to n. And this is, of course, a finite number. I mean, just because we have a finite generating set. So this is less than infinity. And then if you're interested in growth, so this is the arithmetic. This is kind of the counting the number of words. And if you're interested in growth, then of course you look at what has not been introduced yet, but it's called the summative function Sn. And okay, let me write this once. This is sum k equals 0 to n a dot k g. So this is the growth function, and I said I wouldn't, but I'll put the s's in for once. So you see, this all depends on s. Then you can make up your mind whether this is confusing or not. This s, different s's. Okay, and there's another s here. Right. Okay, and this has a geometric interpretation in terms of looking at the Cayley graph, of course. Yeah, so we can write down the Cayley graph of this group with respect to this generating set, and then this would be doing something like determining the volume of the n ball, kind of around the, well, any point really, yeah, but let's say the identity, and this would be sort of counting, or this would be giving you the volume of the sphere, the n sphere. Okay, so these things are related, and you can compute the a n's from the s n's and vice versa. Okay, now I want to start this series of examples, and I'll leave some space, hopefully I managed with the boards, to fill in the subgroup perspective later on. So the very first example we saw already. So the very first example Christoph already talked about is this group. It's a Abelian group on two generators, Z cross Z. And let's stick to the standard generating set. So let's stick to the generating set. Well, that in my notation gives this. Okay, and let's draw a picture. So this is a lattice in the Euclidean plane, and so the lattice points are these kind of grid points. And the spheres look a bit like this, right? So this is what in this word metric, this is what the distance tells me. So these are the 4 points of distance 1 of the origin, let's say, and these are the 8 points of distance 2, etc. And we already know that it's a good idea to express things in terms of generating series. And so if in this business, in the business of the word growth, one is mostly interested in these numbers. And one produces generating sequences in terms of these numbers. And so if you do that here, so this all depends on and let's take some variable z. So you produce an ordinary generating function, and well, I guess you've seen this before. So you get something like 1 plus 2z plus z squared divided by 1 minus z to the 3, I guess. And this is a small exercise. Of course, this is not difficult to do. And this somehow has another interesting geometric interpretation. So if you start with this kind of polytope, this kind of two-dimensional polytope, and you scale it and you sort of count integer lattice points that you see inside such a scaled polytope, this gives rise to what's called Erhard theory. And so there's a whole kind of business for this. And so this is the same as what is called the Erhard. This is called the Erhard polynomial, and this is kind of the Erhard series associated to a certain polytope. In this case, it's this polytope here, and it has a name. So there's a general theory for this. So this is the Erhard polynomial, which usually denoted W of Z, or at least I denote it by that. And there's always a dimension thing here. So we're in dimension 2, so this is d plus 1. And this is a polynomial, WZ is a polynomial of degree, as here it's at most the dimension 2. And as this is another feature that was mentioned, so for some maybe deeper reason, these polynomials with integer coefficients have non-negative coefficients. So this is a baby example of some kind of wider theory, where here we're looking at the d-dimension at the d-dimensional polytope, and here I guess his name is the kind of cross polytope of a d-dimensional polytope. Okay, so this is somehow this is an example where we take a very simple, innocent kind of group that we understand extremely well, and we get very strong connections to some combinatorial theory. In this case, this kind of Erhard series of d-dimensional, it's a d-dimensional cross polytope. So here, this thing here is the d-dimension, so 2-dimension in our case, but it generalizes so-called cross polytope. Okay, and I mean, Christopher showed us what the subgroup zeta function of this group was, and it was also something fairly tame looking, but we're doing different things there. There we were encoding these numbers, yeah, I mean, the analog of these numbers, and we were looking at Dirichlet generating series. So there was a kind of slightly different setup, okay? Okay, now, I'm not sure, I don't think Christopher mentioned this. So the second example that I'm going to look at in this lecture is kind of generalizations towards nilpotent groups. So if we go away from Biel in a little bit, so the first kind of example to look at is perhaps the discrete Heisenberg group. So this is a very interesting kind of example. So this is upper unitriangular matrices with integer coefficients. So it's the kind of Z points of a rather special unipotent linear algebraic group. Okay, so it's a lattice. This was a lattice in the, lattice in the kind of geometric sense in the abelian, in the Euclidean plane. Here we have some kind of lattice in terms of some real kind of Lie group. Okay, so I will denote this by H1, hopefully. I mean, it's not going to come up very often. So this is called the Heisenberg group, this discrete Heisenberg group. And it happens to be, so it has different, there are different reasons why people are interested in it. So the name gives away maybe one reason. That's not the reason I'm interested in it. Somehow it has something to do with Heisenberg. But for me, so this is the free class 2 nilpotent group. On 2 generators. So if you put in a 1 here and zeros over here, or you put in a 1 here and zeros over here, you get 2 generators. The commutator is the matrix that sort of has a 1 here and zeros down there. And that sort of explains how this becomes a class 2 kind of nilpotent groups on 2 generators, and it happens to be the free one. Okay? And you can generalize this parameter, of course, and you can generalize this parameter. There's also a number. It's written as a word, but it's another number. So there's a family, a 2-parameter family of kind of interesting free objects that one might care for. And this is essentially, I think, one of the early examples where the subgroup zeta function was computed, but also, of course, people have looked at word growth. And there's a very surprising result. This goes back to Michael Stoll, 1996, I put down here. Kind of Inventionist paper. So Stoll, it's very surprising. It's a very innocent group. This is like one of the sort of tame groups that we're interested in. So he shows that if you generalize one step further, so forget about this one. Let's look at the kind of different generalization of what I indicated here. You take 4 by 4 matrices. Well, we all know that taking, the upper unitriangular matrix, this gets us into very shaky waters. But do the following. Just generalize in this way. Put a 0 here. So this is a matrix, so it's another Z. This is another matrix group that sort of, you see the pattern, how you get from H1 to H2 and H3. You just fill in the kind of the top row and the last column, and you put zeros anywhere in the middle. This stays very tame. This is like a direct product of copies, in this case, 2 copies of H1. So one comes from these 2 generators, and another one comes from these 2 generators. And you amalgamate the centers. Okay, they have a common center in this group. Of course, if you take the direct product, they don't. But you take direct products and you amalgamate the centers to make the center one-dimensional. You get another series of kind of groups. If you take this group and you play this word growth business, so you choose a generating set. You can imagine you take the nice one, or you take any of your choice, and you write down this kind of generating series, which encodes the word growth. Then for some choices of generators, for this very innocent group, you get a rational expression like that. And for other choices, in particular, I think for the standard choice, you get a transcendental function. It's not even in the algebraic closure of the field of fractions of polynomials. It completely jumps. As soon as you pick, in some sense, the naive generating set, you end up with something that is very far from rational. Okay, so this has generating sets as such that, okay, I didn't give that a name, let's just write it shorthand so that this thing here of H2 Z to the N is transcendental. Yeah, it's not an element in QZ bar. This is the algebraic closure. Yeah, this series is transcendental. Okay, and that's a big surprise. Yeah, somehow. Why should that happen? Well, and it has, of course, it does have generating sets where it is, but it has others, such as and others where you're rational. Okay, so so this kind of thing doesn't happen for H1. So this happens to be a pan-rational kind of thing. The rational function changes with the generating set, but you stay in this kind of tame world. But one step further, you get into messy waters, or maybe very interesting waters. Okay. And yeah, I guess we will look at the subgroup zeta function of this either during the lecture or maybe in the tutorial. So this if you compute the subgroup zeta function of this kind of group using the ANs and using the Dirichlet series kind of approach, which is independent of any choice of generators, you end up with essentially some kind of product of shifted Riemann zeta functions divided by another kind of shifted Riemann zeta function. Okay, so but for these groups still kind of the world looks good. There's another blackboard there. So the next step is to go from nilpotent to solvable. And for solvable groups, things get very quickly kind of out of hand. So the third type of group I want to look at. So this is the Reef product C2 Reef Z. So sometimes it's called the lamplighter group. So there's also kind of there are generalizations, so you can replace 2 by another prime, or you can do sort of more fancy things, but this type of groups, they're called lamplighter groups. So let me write down a presentation, and then if you know what a Reef product, everybody knows what a Reef product is, but let me just remind myself what this is. So it's a group on 2 generators, it's a 2-generated group. The first generator has order 2, and the second generator will have infinite order. I don't do any kind of, that belongs to this, the A belongs to this. And all the things the A's and their conjugates are supposed to commute. So A commute to the conjugated by T to the I, A, T to the J, they all commute for for I and j in Z. Okay, so the group looks a bit like this. So there's a kind of a wide screen thing that, on this blackboard, I could even write it. I mean, it's and then there's a kind of very thin kind of Z on top that kind of permutes this kind of coordinates. This is what it looks like. And sorry? What is the multiplication? Well, it's A times T is A times T. So, it's conjugation. Sorry, this is T to the minus I, A, T to the I. Just conjugation. Okay? So these groups down here, this one's generated by A, this one's generated by A to the T, it's generated by A to the T. So it's a bit like that. So people in the first row can read it. Okay? It's a big vector space and basically one infinite cyclic group that shifts the coordinates. That's what it is. So if you look at this thing, there's a little trick that I can't refrain from writing on the board, even if my time is limited. So of course we take this generating set. So then my thing, I'm looking at words in, well, the trivial element A and T to the plus or minus 1. And so from the picture, at least, or from my description, you can see that this word, so you take A times A conjugated by T, times A conjugated by T squared, etc., times A conjugated by T to the n minus 1. This is a word that I can write in this way, and I use up many letters. I mean, I use the A many times, but because I undo the conjugation, I also use up the T's lots of times. If I just write it as a word in A and T like that, but there's a lot of cancellation going on in between, right? So if I really do all the cancellation, then only one T inverse survives in the middle here, and another T inverse survives over here, etc. So it becomes like that. And at the end, I will get a T to the m minus 1. And that happens to be the shortest way you can do it. I mean, that's not visible anyway. We get a bound for the length of G. So this, with respect to this generating set S, the length of this is, well, we have MAs. So this is equal M, this is for the A's. Then we have the T to the minus 1s. There's m minus 1 of those. And then another T to the m minus 1 here. So another T, the m minus 1 here. So this is linear in M. Yes, linear in M. But now what you can do is you can decide to, I don't know, leave out some of these A's. Okay? So as an element in this vector space, this is just like an element 1, 1, 1, 1, 1, and you can leave out some 1s. So you can write zeros in those places, and you get different elements. And the length, of course, doesn't decrease if I leave out some of these A's. So I get, within linear in M kind of distance from 1, I get 2 to the m elements. So that means we have exponential word growth. Okay? So leaving out some A's. This will show that the number of elements in word growth for this generating set, this group G of length, well, it's 3m, let's put 3m, and there's a minus 2. Well, this is greater or equal to 2 to the m. So this is linear and this is exponential. So that means we get sort of exponential growth. So we are in exponential growth. Okay. And so that means that even if we are solvable solvable length 2, it's very tame. Abelian, this is abelian and bi-abelian, we can become exponential. Of course, the reason is that this vector space down here is infinite dimensional, right? So this means that the Prüfer rank of this group has kind of exploded. That's not the reason, particular for word growth, why we get into trouble. But that's the reason in subgroup growth why we might get into trouble. To have these kind of abelian but very large things, even though the whole group was finitely generated. Okay? Okay, now you can study, of course, then groups of exponential growth, and that's interesting, and there's some kind of parameters. And I mean, the next example, of course, on my list is free groups, and that's again something. So here it might not be so easy to compute explicitly what happens. But so another example, it's very small. Let's put it here. It's kind of free groups. So there again, it should be very easy to compute. Fourth example, if you go even bigger, so if G is a free group on D generators, free on D generators, D is greater or equal to 2, then of course we will map onto this thing, so we better have exponential growth, but it doesn't get worse, so it doesn't get super exponential. So we also end up with exponential growth. So we still have exponential growth, word growth. Okay, so that's the and you can write down a nice formula for that. So that's what I wanted to say in terms of examples, and we'll sort of go through them again in terms of subgroup growth. But there's one more thing that I want to highlight before doing that, and that's because to draw the line and then make the analogy to the kind of subgroup growth where we have nice kind of Dirichlet series. And so these were the ones where you have polynomial growth. And so this also happens, of course, in word growth. And there's a famous theorem of Gromov, which somehow describes these groups. So let me just mention that because it sort of provides some background. So there's a definition. So let G be a finitely generated infinite group. So in all of this, you might be interested in finite groups, and there might be something interesting to discover, but I will not say very much about it. So I'm afraid that's for others to speak about. So let me sort of put infinite here. So the definition makes sense. So we say that G has polynomial word growth. So that's, well, as you imagine, that just means that the summative function Sn of G with respect to some, and then for every, this is sort of not depending on the set S chosen. This grows at most polynomially. Grows at most polynomially in M. Okay, and so there's an interesting invariant that one can define. So it's the degree of growth. So this is the polynomial degree of growth. So if you want to extract the kind of smallest exponent, then what you should do is you should take logs, right? So you should take the logarithm of this thing that you know or expect to grow polynomially, and you should scale so that you can extract that exponent, and then you take the lim sup of that, and if that happens to be finite, then you say you have polynomial growth. And so there's another S coming up here. So that's this S, but really it does not depend on S. So it turns out that this is an invariant. This is independent of S, independent of the choice of S. So this is a good invariant. The degree of polynomial growth is a good invariant in that business. This is the degree of growth. Of word growth. And this is an exercise, so it's probably something we could do in the tutorial. If you have never done it, it's very instructive. There's no claim. This is a definition. The generating set. So if you pick different generating sets, the whole counting business could stop. but the degree of polynomial growth will not change.
So you were saying that for one S, one particular S, if it grows polynomially, you're saying for all S, it will have that property?
That's right. It will still grow polynomial, and you will get the same degree. So whatever you compute here, it will be the same. If it grows quadratically with one, it will grow quadratically with any other generating set. Yes?
So is that easy to see?
That's an exercise. We will discuss it in the tutorial if you want to. Yeah. It's I mean, this whole business, I don't have time to mention, but it's the growth type is kind of an invariant under what is called kind of it's from I mean, you can also factor out like finite quotients, and you can sort of put something finite on top. So there's some kind of geometric notion of almost homomorphisms. And so if these things are almost isomorphic in some sense, up to word length kind of, then these growth types don't change. Okay, so the reason I'm mentioning this, so this is the degree of growth, this is the polynomial degree of growth. So the reason I mention this is because there's a formula for that. So in the world of word growth, this is an easy invariant. I mean, once you've identified the groups of polynomial word growth, and I will tell you, Gromov told us what they are. And now with examples, okay, I can. Yes, please. These are examples of groups with polynomial word growth. So I will write it in a moment, but these are the finitely nilpotent groups. Yeah. So every finitely nilpotent group will have kind of polynomial word growth. So I'll write it now, sorry. So keep that for later. So this is a theorem which goes quite a way back. So I think this is Hyman Bass from the 70s. So I put 1972. So if G is a finitely generated nilpotent group of class C, and if you then look at the lower central series, and you look at the torsion-free ranks, so I'll explain that. I'll write it down, and I'll explain it again. So of the sections of the lower central series. Okay, so this makes sense because we have class C. This makes sense to do this for I between 1 and C, and then it becomes 0. I mean, it's nothing. Then you can form from these, you can form the following parameter, R. So it's the sum of these numbers, Ri, but each time you multiply by I. This looks a bit reminiscent to what Christopher did somewhere over there on the board, and we couldn't read, but somehow here. And so then there's a stronger statement. I will, for the sake of time, I will kind of not give you the stronger statement, but in particular it will say that this group G, well, it has polynomial word growth, and we know what the degree is. It's just this number R. And so you can compute the degree of polynomial word growth very easily once you understand the lower central series. Yeah, so the lower central series is this thing that goes down like that, just the commutator subgroup. And then you commute again with, I mean, this is gamma 2 G, etc. So, and by definition, when we are class C, we've seen the bottom when we reached C plus 1. So this is 1. And so these sections, they are central in the kind of bigger group, but they're in particular abelian. They're finitely generated because my group was finitely generated. And there might be some torsion kind of sitting around, but when I tensor it with Q, I just sort of destroy the torsion. So that's just sort of counting this like the finitely the torsion-free rank of this kind of finitely generated abelian group here. And if you multiply each one of them depending on where they appear in your kind of skyscraper, then and you add them all up, then you get your growth. Okay, so things things on the bottom contribute more than things on the top. And yeah, and that was known in the 70s, and I mean the famous result by Gromov is that these are, I mean, essentially these are the groups of polynomial word growth. So let me just write that. I'm not about to write any. Well, could I write? Well, okay. Maybe there's someone watching us. So, okay, so yes, please. We're doing word growth at the moment, so bear with me. So the previous, sorry? It's not, yeah, I wouldn't call it a zeta function, so it's a generating function, and there aren't any, I mean, there aren't any local factors, so there's no arithmetic in this business at the moment. I mean, I don't know, I don't think there is, because this group, that's one of the differences between subgroup growth and word growth, that somehow the arithmetic sort of comes in. Yeah, we'll see that, yes. So this famous theorem of Gromov. So G finitely generated of polynomial word growth if and only if, well, G is finitely generated virtually torsion. Finitely generated we already know, but somehow it's virtually. So this is the interesting direction. The other direction is not so interesting. So if you're finitely generated of polynomial word growth, then you are virtually nilpotent. And this term may come up again, so i.e. this means a finite subgroup is a finite index subgroup is finite index, so up to finite index. Finite. Oh, the Indian chalk is much harder than the German one. Group is, so let me take the German one. Right. Okay, so up to finite index, so you cannot expect your group to be nilpotent on the spot, but there will be something of finite index, which is, and of course this will again be finitely generated because the G was finitely generated. And then you can apply Buss's theorem, and you get sort of this degree for H, and then you see it's the same. I mean, it doesn't change. Okay. So this sort of settles the word growth business completely for polynomial word growth, because we have this nice result. It was known before, this was Milner's theorem, that if you're solvable and you're not nilpotent, then you will end up in this category. You will be of exponential word growth. Okay, and then there was a big question whether there are actually things between exponential and polynomial, and there are, but I won't talk about these Grigorchuk's examples. Okay, there's an interesting ingredient. I mean, there are several ingredients, but well, he also invented a lot of new mathematics, but there's some interesting ingredient, small kind of piece ingredient in this Gromov theorem, which is kind of Jordan's theorem. And we'll meet that again when we talk about representation growth. So Jordan's theorem says that if you're a finite linear group, then you are boundedly abelian. I mean, depending on the size of the matrices. So it's a bit like virtually, but sort of translated in a quantitative way into the world of finite groups. So these kind of results where you sort of virtually something, they sometimes come from, you know, going to finite quotients or finite groups and then having sort of explicit bounds. And then they kind of materialize into these results. Okay, I won't write that down because I'm afraid I'm going to run out of time. So now let's turn to subgroup growth, which is our business. So sorry for doing this, but I will have different types of groups coming up now. And so I will sort of slightly adapt my notation. So my main group at the moment will now be called gamma. So we'll now talk about groups gamma and certain other groups that maybe are topological groups or kind of things that I derive from gamma, they will become Gs, okay, or some other groups that I will talk about. So if you've never seen this, then I apologize. And I mean, now my group, so to speak, that was called G up to now, I will sort of call gamma. Okay, so it's a finitely generated group. And then, well, we were already told well, I'll tell you again, that we could be interested in enumerating things from the top rather from the bottom, rather than picking some generating set and counting how many elements we can produce when we sort of step away from the identity element. We could sort of look from the top and try and filter things from the top and look at sort of finite index subgroups. And so, as Christopher defined them, so we get these numbers an of gamma, which is the number of subgroups. I will call them delta now. So these are subgroups of gamma of index precisely n. N is some natural number. And because I'm finitely generated, it's also a good exercise or something we could discuss in the tutorial, these numbers turn out to be finite. This has to do with the fact that when you have a finite index subgroup, you get a natural transitive permutation representation on, well, on the cosets, and there are n of them. And so essentially you're looking at homomorphisms from your group into Sn, into the symmetric group on n letters. And if you're finitely generated, there are only finitely many of those. So these are finite numbers, it's a bunch of finite numbers. They form an arithmetic sequence. And we also have the Sn of gammas, and again, these are the summative things, and of course they are finite numbers. And they basically just are an alternative way of looking at the data. But this is the kind of thing you want to look at in terms of growth, and this is the terms you want to look at in terms of arithmetic. So this determines this, and this determines that. But it's good to have both on board. Okay, so this is then what is this kind of, this determines the subgroup growth of gamma. Okay, and well, I told you there's going to be some G's coming up, so so we will inevitably at some point start talking about these kind of p-adic groups and kind of profinite groups, so special profinite groups. So here's an aside. So this gamma, this has a natural map, canonical map into its profinite completion. So the profinite completion is, well, some inverse limit construction. It's a way to look at all finite quotients of that group at the same time. So I'll write little f here to denote that the index is finite. So this runs through all the finite quotients of gamma. And there's a way, if you've seen this, then it's easy peasy. And if you've never seen it, then I will tell you maybe at some other stage. There's a way to string them all up and to form a big group, gamma hat. This is called the profinite completion. And this is one of these groups that I will typically denote then by G again. And it turns out that this has a topology. This has a natural topology. It's a kind of compact group with a natural topology. And because we're in the topological world, it doesn't make sense to look at all kinds of subgroups. It's like an infinite Galois theory. You look at the closed subgroups. So we look at the closed subgroups of finite index. Closed subgroups of finite index are open. This is an easy thing to see from the definition of closed and openness in topology. And so you can count in that group G the open subgroups of a given index. And this turns out to be the same. So this A n gamma thing I was interested in the original group is the same as the A n G, where now, because I'm a topological group, by definition, this is the number of H's such that H is an open subgroup of G of the corresponding index n. So there's a one-to-one correspondence between these things and the kind of original subgroups in gamma. Okay, and that opens up some new, I mean, it doesn't change anything, but it opens up some new technology that you may imply, at least in terms of language. You can now use topology somehow. And ask, is this a p-adic analytic group, or can I somehow relate this to some other nice topological groups that I know something about? Okay, and yeah, this map, this is a canonical map, this may not be injective. In general, it will not be injective because it will not be true that the intersection of all these kind of finite index normal subgroups is trivial. But that is the only part of the group that we care for because these are the only numbers that we see. So when we study subgroup growth, we want to explore groups in terms of these numbers, we only talk about a quotient of gamma, namely gamma modulo the intersection of all these kind of finite index normal subgroups. That's called the finite, the finite residual? It's the finite residual of gamma. Okay, and so this is a term that might come up again, at least when I formulate theorems. So keep in mind that somehow in word growth, this kind of polynomial growth things were well under control. How much more time do I have? Anybody keeping? Sorry? I run over time.
So what do you want coffee?
Ah, shall we stop now? Sorry. Seriously, I should stop soon, yeah? Okay, I should stop soon. Okay, let me at least finish this definition and look at one example. Okay, can you hold out another 5 to 10 minutes? Is that okay? Am I? Okay. Otherwise, you complain. Okay, so so we may restrict. So we may restrict to gamma being residually finite. And that means that the intersection of all these deltas, delta normal of finite index and gamma, is trivial. Yeah? And the reason being that somehow that is a normal subgroup, this kind of finite residual is a normal subgroup, and so we only see this group anyway, and this gives rise to G, and all this we will never explore. Okay. Okay. There's one more thing I wanted to say in this regard. This also makes the problem harder, I mean, if we go to profinite groups, because there are more profinite groups than there are profinite completions. Okay, so not every profinite group is a profinite completion. So that makes sort of the world a bit larger, has advantages and disadvantages. So we can produce more examples, we can develop new theories, but not everything will sort of be tied one-to-one to the original problem, maybe with the abstract group. Okay, why don't we have coffee here? And then I will continue afterwards. So. Lunch.